Okay, so that is the resolution issue. Another very important thing for data acquisition is sampling frequencies. The higher the sampling frequency is, the more samples we take within a specific time. Right? So basically the sampling frequency, or sometimes called sampling rate, is the number of samples obtained in 1 second. Right? And it can be calculated, sampling frequency equal to 1 over t, with t as the time interval between two adjacent points. Right? Now, everybody knows with a higher sampling frequency, we're going to get a better waveform. We're going to get better data. And more data, of course, more data. Now, what is the threshold? Here we comes with Nyquist sampling theorem. What does Nyquist sampling theorem say? Basically, it says the lowest sampling rate you can use needs to be 2 times the highest frequency of your signal. Let's think about this, right? We have a sine wave. We have a sine wave. And if we take only 3 points, we say this sine wave with a period of 1 second. Period is 1 second. So its frequency is, if period is 1 second, period is 1 second, then frequency is 1 hertz. Right? Frequency is 1 hertz. 1 hertz basically means, in sampling rate point of view, means 1 point per second. Okay? So let's think about this. Let's think about this. If we use a sampling rate, of 2 times our frequency of the signal, we have 2 hertz. At this time, we're taking 2 points per second, which is this point and this point. 2 points, right? They have to be at a constant time interval. So what we eventually get is a waveform like this. Not very perfect, but still we keep the frequency content. We know, we can see it's doing the right stuff. Okay. Now, if we use a sampling rate of 1 hertz, which is lower than what is required by Nyquist sampling theorem, lower than our Nyquist rate, basically. 1 point. So we're taking this point. And by looking at that point, we know nothing. Right? It's just a point. We don't know anything about this waveform. Okay? Now, of course, if we use a high, very smart Siri. Okay, if we use a higher sampling frequency, of course we're going to take more points. We can take more points. Now we see our data after sampling gets closer to our original waveform. to our original signal. So this is why a lot of the time a higher sampling frequency is always preferred, right? If affordable, of course. So this is the concept of Nyquist rate. Okay? When you're taking the data, you always need to pay attention to the sampling rate. The reason is, if the sampling rate is too low, then you're ignoring a lot of useful information. You're losing a lot of useful information. Now, we cannot confuse this Nyquist rate with another concept called Nyquist frequency. Nyquist frequency basically is defined as 1/2 of the sampling frequency of a digital signal. It's nothing related to AD converter. Okay? Okay, now here comes aliasing. Aliasing, actually, we already introduced a little bit. There is an effect that causes different signals to become indistinguishable. What does it mean? It causes different signals to show up as the same waveform after sampling if we use a sampling rate lower than Nyquist rate. Right? So you can think about this. We have a high frequency waveform, the red one, and we sample it with a very low sampling rate. So we take these points. 1, 2, 3, 4, those points. After we take them out, we plot it. Now we see, this is a very nice waveform. Looks right to me, but no. What's actually happening is, because we have a sampling rate much lower than Nyquist rate, we're actually building a different waveform out from these points. And we're looking at completely different stuff, which is the blue curve. So when you compare the blue curve to the red curve, you notice, that's a lot different. So this is aliasing. And of course, when we sample this blue curve with the same sampling rate, because the blue curve has a much lower frequency, with the same sampling rate, we're going to get the same points. Eventually, the effect is, if you have two signals, one is on the red curve, one is on the blue curve, and you sample them with this same sampling rate, you get same curve, which is the blue curve. Okay? So this is aliasing, and it's definitely something we want to avoid. So whenever you're doing data acquisition, make sure your sampling rate is higher than Nyquist rate. And if you want to coming back to here, if you want to have a nice looking waveform, a good waveform, your sampling rate, based on my experience, it needs to be 10 times of Nyquist rate. If you want to have a nice waveform, it needs to be at least 10 times of Nyquist rate. Okay, so this is simple introduction to data acquisition. Now we talk about digital signal processing. Actually, I have a typo there. It's not data signal processing. So first of all, we'll review a little bit Fourier series. Why do we want to review Fourier series? Because it is related to one very important tool in digital signal processing, fast Fourier transform. And fast Fourier transform is useful because we want, a lot of the time people want to do frequency analysis of signals. They want to see what is the frequency content of this signal. Now, we'll also introduce you guys digital filters. Knowing the frequency content of a signal, we can, based on the frequency content, design filters, obtain a specific frequency out from our signal. Filter design in MATLAB. Of course, if we, this is just an application of our digital filters, okay? Okay, Fourier series. Fourier series, very easy. Basically, it says any periodic functions can be represented by an infinite series of sine and cosine. And this infinite series is this, with a constant term and infinite series of sine and cosine. Now, we observe this signal, this series. We know that as n goes from 1 to infinite, the frequency of our sine and cosine changes. And the frequency is integer multiple of a base frequency, omega. Okay? So, what is our base frequency? Omega is equal to 2 pi over t. T is the period of our periodic function. And then you can calculate all those constants. Here I'm not going to go through all those integrals. But based on this Fourier series, what we can do is, we notice we can represent a signal with, when we rewrite them into a Fourier series, we can represent a signal with these constants. So a Fourier transform, what it does is basically representing a signal in frequency domain with the constant A and B. Of course, when we talk about A0, we only have A0 and B0 equal to 1. Oh, A0, we only have A0 and B0 equal to 0, right? So we can have AN and BN with A0 equal to the constant term, BN equal to 0, B0 equal to 0, and all this combination of AN, BN can be put together to represent the frequency content of a signal. So this is how we achieved a Fourier transform. Now, a Fourier transform, official definition, a mathematical transform that represents a signal with the corresponding coefficients in Fourier series we just mentioned, right? Now, what about a fast Fourier transform, FFT? A lot of people, you guys probably heard about it many times, FFT. Fast Fourier transform is a discrete implementation of Fourier transform. Why do we need a discrete implementation? Because all the signals in our computer, they are discretized. And if we want to apply Fourier transform on discretized signals, then we need a discretized algorithm. Okay? So think about a random signal. This is a random signal. And then if we apply FFT to it, we'll be able to see different peaks. These peaks represent the constant terms AN and BN. Right? Here we know our random signal contains a frequency of 100